Okay. Let's quickly talk about this new topic, which I think I'm just not going to put it on the exam at all, but I want to introduce it because it's going to be first and foremost in 2.2, and it's very necessary because it's going to fill in some gaps. First of all, valence bond theory that we just went over, all the hybridization stuff. Lewis structures is included in that, even though we didn't explicitly say so. That whole idea of the electrons are localized between two atoms, that's all valence bond theory stuff. There are problems with it. First of all, resonance structures is a band-aid, right? This resonant hybrid idea is a band-aid for really what the true picture of the molecule looks like. We can't really describe with proper Lewis structures what a 1.5 bond in ozone looks like. So there's a lot of failings of valence bond theory that we need a different model, a different theory of bonding to account for. And that's where molecular orbital theory comes in. So I'll show you one more failing of valence bond theory. And we're going to watch a little video. And I like it kind of the whole thing, so just watch it the whole thing. Hold on. It's not very long. That works. No? Okay, one second. Come on. Yeah, that's right. This is a Harvard guy.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled Dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet, and then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
I think we've seen this, but this is high resolution one. So it stops bubbling when the copper pipe is cooled down enough. Oxygen and pass oxygen gas directly through the coil. You're not blocked by that. That stuff is super dangerous. Super dangerous. Pure oxygen will cause things to burn very, very easily. Got a faint bluish blue color. Yeah, sort of. Yeah. Not exactly. Maybe different. They poured nitrogen through. Nothing. Gotta get more liquid oxygen through. Very clearly collect. It disappears pretty quickly because the magnet's warm and it's boiling away really quickly, but it's definitely collecting right in that gap. Very strong magnetic field. So what do we call substances that are attracted to a magnetic field?
Polar?
Yes, to electric field. To a magnetic field, it's paramagnetic, right? That's the word we use. So, yeah. Here's the thing. We studied paramagnetism and diamagnetism for atoms, but this liquid oxygen is not atomic. It's a molecular substance. It's O2. Same thing with N2. So really we don't know, so what do the electrons look like in a molecule? Are they paired? Are they unpaired? Remember, so to be paramagnetic, it has to be unpaired. So they're obviously in oxygen, there's some kind of unpaired electrons. Even though it's a regular molecule, it's pretty stable, there's some kind of unpaired electrons. And this is the point I'm trying to make, is that here is the Lewis structure for O2. I don't see any unpaired electrons in this Lewis structure. So valence bond theory fails at this too. It doesn't predict paramagnetism, diamagnetism. So, according to the Lewis structure, it looks like it's diamagnetic to me, but it's obviously not from the video. So we have to come up with this new concept of bonding, a new way to describe bonding. And this one's a lot harder to kind of wrap your head around. It's less visual, like Lewis structures are very easy to see. So this one's going to be along the lines of how we did hybridized orbitals, if that helped. So let's go back to basics. Remember that our wave functions, these equations that describe the orbitals, are basically three-dimensional waves. And if they behave like, so the electrons behave like waves, we can treat them like normal waves. So remember, this is a one-dimensional wave, but if I have two waves and I combine them into one, if I add them together, I can get constructive interference or I can get destructive interference. And the same applies to orbitals. We saw that with the hybridized orbitals. I think I showed, maybe I didn't show you guys, but I showed the other class, sp hybridization. So sp hybrid orbitals, where do they come from? They come from an s orbital mixing with one p orbital. And the one thing we kind of gloss over, we don't teach you guys at this level, is that these orbitals have phases, just like waves have phases. So there's an up and down part to a wave. The same thing happens with an orbital. And so if I call this a up phase or a positive phase, and then this has a positive and negative side to it, when I combine these two, these parts will constructively interfere, and then these two parts will destructively interfere. And so I get an orbital that kind of looks like that. There's an sp hybrid. And the other combination is when I subtract one from the other, and if I do that, I get the other version. So that's where these sp hybrids come from. It comes from treating these orbitals just like waves. They constructively and destructively interfere. But that's hybridization. So, and that's with orbitals on one atom, right? These two orbitals came from the same atom, like acetylene, C2H2. The carbon atom has sp hybridization in it. Well, we're going to extend that to the whole molecule. So we're going to take, for instance, two hydrogen atoms that bond, and we know that already, they make H2. How do they do it? Well, they each use their 1s orbitals. Okay, so this is basically two different hydrogen atoms, one here, they using the 1s orbitals to overlap. And the two ways they can overlap is in phase, where the two orbitals will constructively interfere, or they could overlap out of phase, where one will destructively interfere with the other. And when you put those two pictures together, you get a new orbital that is a combination of atomic orbitals, where you have electron density between the atoms. And we call this a bonding molecular orbital now. It's an orbital that spans the whole molecule. And then the other example, you get destructive interference, where you have 0 electron density between the atoms. And that's an anti-bond. It's like the opposite of a bond. If you don't have any electron density between atoms, it's the opposite of a bond, basically. So we call it an antibond, and an antibonding molecular orbital. So these are atomic orbitals. We're making a distinction here now. And these are new molecular orbitals created from the atomic orbitals. So with hybridization, the rule was the number of orbitals you mix together, you get that number of hybrid orbitals. The same happens with molecular orbitals. So if I combine two s orbitals, I will get two molecular orbitals. We typically label the molecular orbitals with the kind of bonding overlap they're doing. So we learned sigma. Sigma bonds are end-to-end overlap. They overlap in one spot. And if it's an anti-bonding orbital, we denote it with a little asterisk, a little star. So sigma star denotes the anti-bonding version of that overlap, okay? So, you know, we're making it complicated already, but there's a reason for it. So now, what do we do with those? Well, let's look at what these molecular orbitals, where they show up on an energy diagram. So here is the original 1s orbital from a hydrogen atom. Here is the other 1s orbital from the other hydrogen atom that's making the bond. And they are the same energy because they're the same kind of atom, they're the same kind of orbital. When these two orbitals come together and interact with each other, they can make a bonding molecular orbital or an anti-bonding molecular orbital. What happens to the energies of those new orbitals? Well, the bonding molecular orbital is always going to be lower in energy than the original atomic orbitals. That's why they make bonds, because it lowers the energy of the molecule. The anti-bonding molecular orbital is exactly the opposite energy. It's going to be higher in energy than the original atomic orbitals. Okay? And then where do the electrons go? Well, this hydrogen came with one electron. This hydrogen came with one electron. You have a total of 2 electrons, just like we do count for Lewis structures. I'm going to put those 2 electrons in the lowest possible molecular orbital. They're going to go in here. This one's going to be empty because I don't have any more electrons. So what do I do with this picture? Well, so I talked about this. So what do I do with this? Well, let's keep looking for a second. And we saw the example with hydrogen. You're going to put those electrons in the lowest molecular orbital here. So we've gotten rid of the atomic orbitals. We're just looking at the molecular orbital picture in the middle. If I put 2 heliums together, it's going to have the similar pattern as hydrogen because 2 heliums, they also have 1s orbitals, right? Those are going to overlap just like the hydrogen's 1s orbitals would. They'll create a similar kind of pattern like this, a bonding and an anti-bonding molecular orbital. What's different between them is the number of electrons. So helium-2 plus, if I imagined helium-2, not plus, not star, sorry, plus, this thing has 3 total electrons. Each helium comes with 2 electrons, and the plus means you're missing one of the electrons. So instead of 4, there's 3. So when I fill my molecular orbitals with these electrons, I'm going to start from the bottom, just like normal. I put the electrons in the lowest orbital possible first. 1, 2, and then the third one will have to go into the anti-bonding orbital. Regular helium, this seems weird, right? He2, nobody has ever seen a bond between 2 helium atoms. Well, if I follow this example, if I try to overlap 2 helium atoms, just plain atoms, I'll still get the bonding MO and anti-bonding MO, but I'll have 4 total electrons to put in. So I'm going to put 2 down here, and then 2 up here. Now, next, bond order. So this is the advantage of molecular orbital theory. We can calculate bond order a different way than we do with valence bond theory. So to calculate a bond order from MO theory, you are going to add up electrons in bonding MOs, bonding and molecular orbitals. You will subtract the electrons from anti-bonding MOs, and then you multiply by a half, so divide by 2 in the end. So when you do it for hydrogen, right, you get 2 electrons in bonding MOs, you get 0 electrons in anti-bonding MOs. 2 minus 0 is 2, times a half is 1. Bond order 1. Let's see, we know that already. Valence bond theory predicted that. Our Lewis structure of hydrogen looks like this. That seems overly complicated just to figure that out. But here's where molecular orbital theory shines. We've got this weird molecule, He2+. And if I calculate the bond order for it, I actually get a bond order of 1/2. 2 minus, so 2 electrons minus 1 electron in anti-bonding MOs times a half gives me a half of a bond. So this weird thing actually can exist. if I take a regular helium atom and another helium atom and ionize one of them, remove an electron from one of them, that ionized helium can make a weak bond with regular helium. That's what this is telling me. And then if I look at the weird one, this He2, 2 minus 2 times a half is 0. We knew this. Helium doesn't make bonds. But here's the confirmation via molecular orbital theory. We have 0 bond order. So this is one of the advantages of MO theory. We are doing really simple molecules. So for H2 and He2, we knew the answer already from valence bond theory. But we would never have known the answer here using valence bond theory. All right, so there are special cases to use MO theory, and there's going to be cases when valence bond theory is fine too. Valence bond theory is the easiest way to do it. But, okay. So like I said, we can get more complicated. Here's, if you're a Star Trek fan, dilithium. 2 lithium atoms, can they make a bond? Well, you do the MO picture for it, and here are the inner electrons. We can kind of ignore those. They're always going to be net 0 if you do the calculation. So here are the valence orbitals, the S, 2s, and the 2s, each with 1 electron. If I calculate the bond order for this thing, I can use the whole thing. 4 electrons in bonding MOs, 1, 2, 3, 4. 2 electrons only, so there's 2 in antibonding MOs. 4 minus 2 times a half is 1. So you can make a bond between 2 lithium atoms. Now, we're going to find that it's more complicated than this. Lithium's a metal. You can actually make many bonds. You can have a whole bunch of lithiums, but we'll see that in 222. And we're going to use this MO concept in 222 to show why conductivity works, to show how LEDs work. It's going to be an important part of 222. So let's throw in p orbitals. What do p orbitals do in MO theory? Well, they can do end-to-end overlap and make sigma bonds, but they can also do side-to-side overlap. So remember, if I have 2 atoms, if I have 2 carbons side by side, each carbon has 3 different p orbitals. All right, one will be pointed right at the other. They'll do this kind of bonding up here. But then each carbon also has a p orbital going up and down, and a p orbital going in and out of the screen. So I can do 2 kinds of pi bonding with each carbon. So when I expand this out into molecular orbital theory, this is going to, you're going to be like, oh my god. Ignore this. This is the inner. We're going to look at this part. This is the valence. Here is the 2s. Here are the 2 p's of one, for instance, carbon or nitrogen or oxygen, any one of those elements. Here's another atom with the 2s and 2 p's. The 2s's can overlap to make bonding, antibonding, just like we saw before. The 2 p's, they can overlap end-to-end and make bonding or antibonding end-to-end overlaps, or they can do side-to-side overlaps, bonding, antibonding. Now, don't worry about it. You don't have to memorize this, anything. Just those are all the different interactions these orbitals on separate atoms will do. Let's fill these up now and see kind of what we can see. This is basically saying that the position of these boxes, these orbitals, can change depending on the identity of the element. So sometimes you'll see a slightly different pattern, but essentially this is kind of the thing you see. So you'll get these diagrams. Don't worry, you don't have to come up with these on your own. Not until you get to grad school. And then you have to do, if you're into math, you'll have to learn this math called group theory, where you take a molecule and you say, well, what are all the different transformations I can do to it to make it look the same? I can rotate it in third increments and it looks the same. I can mirror image it this way and mirror image it this way and it'll look the same. And if you combine all of those transformations, you can come up with these things. It's really weird math. But it's fun. It's new. So let's do a sample carbon-carbon bond, and then a sample nitrogen-nitrogen bond. This is showing all of the electrons, not just the valence, okay? So for carbon, carbon has a total of 6 electrons. All right, 4 valence electrons, but total 6. So if I have 2 carbons, that's 12 total electrons, 6 from each. So if I fill that MO diagram from the bottom with 12 electrons, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the MO diagram for a carbon, a carbon-carbon bond. What do we know about unpaired electrons and paired electrons? Well, this is going to be diamagnetic. That's what this MO diagram predicts. I don't see any unpaired electrons in this diagram. Everything's paired up. And as far as the bond order goes, well, we'll get to that next. For nitrogen, nitrogen is element 7. It's got 7 electrons total. So 2 nitrogens is 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Nitrogen, N2 is diamagnetic as well. That's what we saw in the video. When they poured liquid nitrogen through the magnetic field, it just went right through. It was kind of, it was not attracted to it. So as far as bond order goes, two carbons by themselves have a bond order of 2. How do we know that? Well, I can count electrons in bonding orbitals. 1, 2, 3, 4, 5, 6, 7, 8. Anything without the star is a bonding orbital in this case. And then anti-bonding orbitals, 1, 2, 3, 4, and that's it. So 8 minus 4 is 4 times a half is 2. So it's got a double bond between the 2 carbons. How do you account for that with valence bond theory? It seems weird. Like, I don't know where the rest of the electrons would go. It's hard to predict. This is not a stable molecule. But if you suddenly made this, that's what the bond order would be. With nitrogen, we already know the bond order. Nitrogen, nitrogen looks like this with valence bond theory with Lewis structures. And we can confirm that with the bond order calculation on this MO diagram. There's going to be 10 electrons in bonding orbitals minus 4 electrons in antibonding orbitals. 10 minus 4 is 6, times a half is 3. Okay, now let's look at oxygen. So the pattern is flipped a little bit when you get to oxygen, but here we're looking at just the valence orbitals. All right, we're not looking at the 1s's anymore. So if we count the total number of electrons, valence electrons that oxygen has is 6. 2 oxygens will have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's the unpaired electrons. So that's why O2, when you pour it through the magnetic field, is attracted to it. It's paramagnetic. It's because we have unpaired electrons, and we can verify that with molecular orbital theory. Okay. Everybody's like, oh my god. If I don't need to know this, don't show it to me. Well, I want you to see it so you'll understand why it's important and where it's coming from in 222, if you're taking 222. And I wanted to show it to you because it is filling in some of the gaps. Like, Lewis structures doesn't explain everything. It's not the perfect model. No model is perfect. In fact, one of the popular sayings is every model is wrong, but some models are useful. Which is true. Not every model shows everything exactly the way it is, so they're all wrong. But most of them are very useful. So we've got valence bond theory, Lewis structures, they're useful in certain scenarios. MO theory is useful in other scenarios. So I think that's all I want to show you guys. Well, I mean, so you can come up with some really interesting stuff. A bond between 2 borons, a bond between, here this is the cyanide ion. What are their bond orders? Are they paramagnetic or diamagnetic? So for 2 borons, all right, and we're looking at all of the, so this is the inner orbitals too. Boron has 5 total electrons. 2 borons will have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of a sudden we can see unpaired electrons. This is going to be paramagnetic. And what's the bond order going to be? Well, 2 electrons plus 2 more, 4, plus 2 more, 6 electrons in bonding MOs, minus 4 electrons in anti-bonding MOs. 6 minus 4 is 2, times a half is 1. There's a bond order of 1. A single bond between these 2 borons. And then we do cyanide. Carbon, nitrogen, plus an extra electron from the charge. 14 total electrons. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This thing is diamagnetic. And it should have a triple bond. And we can verify that with Lewis structures too. But yeah, bond order 3. There are other things this is useful for. So we just did a lab today where we looked at IR spectra. And we saw that the IR spectra that we see from molecules comes from the absorption as a vibration. So it causes from vibrations of bonds. But what about the visible side? So we did a whole lab where we looked at absorption spectra in the visible region. Where do those absorptions come from? Well, they actually come from these gaps between electrons in bonding MOs and anti-bonding MOs that have no electrons in them. So the energy to move an electron from here to here will usually correspond to some visible region. So when I put an electron up there, or let's say when I shine light at this molecule in solution, and for instance, it absorbs red. There's a big peak in the red area. That's probably because the gap here has an energy that corresponds to a red photon. And it absorbs that red photon perfectly, okay? So that's where all these visible absorptions come from. And we can predict those using molecular orbital theory. Not with any other bonding theory. MO theory is very, very, very useful. Okay. I'm gonna skip the rest of this. So here's even benzene. We can do crazy MO theory stuff with benzene. Yeah, and that's where these come from. So I don't know if I want to say anything about this. All right. That's all I want to say about this. I don't want to get too far in the weeds. And I'm really serious. 222, you'll start off with learning about ionic bonds. And that'll be easy. That's Coulomb's law. But then you'll get to metallic bonds. And you can only explain metallic bonds with MO theory. So be ready for that. That's like week 2, or week 2.5, week 3, something like that. All right. Next. This is posted on D2L, so feel free to follow along if you want, or ignore me and do it yourself. I was going to do some of the practice exam, maybe the newer stuff, and if we have time, come back to the older stuff. So this is old stuff. I'm going to skip most of this right now, if that's okay. We'll come back to it. Very old, very old, very old. Coulomb's law stuff. Energy of photon, transitions, ionization energies, trends from the periodic table, shell model, quantum mechanical solutions, quantum numbers. We've done all this. Pauli exclusion principle, orbital. Oh, well, I guess. Did we do a test on this? Yeah, we did. Yeah. Electron configuration. We're getting close to where we kind of stopped. So titanium P3 plus, tin 2 plus, electron configurations. Oh, we've reused some of these actually. So 36. Which atom has the largest? No, I guess we did this too. Has the largest number of unpaired electrons. Which ion is the smallest? We've got ion size, bond length. There you go, 39. This is new. So which bond length is the shortest in the following compound? So for covalent compounds, the bond length is going to be simply due to the size of the atoms. So we're looking for the two smallest atoms put together. And carbon is not huge. Fluorine is smaller. It's on the furthest to the right in the periodic table. But hydrogen's even smaller. Hydrogen's tiny. And I've got two hydrogen something bonds. So it's going to be a race between hydrogen and carbon versus hydrogen and oxygen. So the idea is, well, which one's smaller, carbon or oxygen? Oxygen's smaller. As you go to the right on the periodic table, atoms get smaller in general. So oxygen-hydrogen is going to be the shortest bond in this particular molecule. Does that make sense, hopefully? Okay. So hydrogen is just the smallest because of the shell, right? Shell 1. But we're looking at a combination of two atoms making a bond. So it's either going to be carbon-hydrogen or oxygen-hydrogen. In this case, it's oxygen. In which of the following is the carbon to oxygen bond the shortest? So now we're looking at the same two atoms, but the shortest one is going to be the highest bond order, which looks like D. I don't see anything else. So yeah, D is the shortest bond, because it's a triple bond. Triple bonds are stronger and shorter. Which of the following compounds contains the strongest carbon-nitrogen bond? So this is one of those compound problems where you've got to actually do some stuff before you can answer it. You've got to draw these out. And while you're welcome to do Lewis structure rules the long way, whenever you're dealing with kind of simple molecules where they just look like carbon, hydrogen, and maybe a few other atoms like that, do the basic rules where carbon has 4 bonds. Nitrogen has 3 with a lone pair, oxygen has 2 with 2 lone pairs, and the halogens have 1 bond. Just remember that in your head, and that will make things easier to draw. So A, carbon needs 4 bonds. So it's got the hydrogen, and it's next to the nitrogen, and the nitrogen's connected to the hydrogen. So we're missing a bond here, it needs 4. Nitrogen needs 3 bonds, so the double bond goes there. And if you don't see that, try it the long way, feel free, but this is how you draw this one. B, HCN. Well, carbon needs 4 bonds, nitrogen needs 3, so it makes sense to put a triple bond there. 4 bonds to carbon, 3 bonds to nitrogen. And I've already seen the answer. So there's the answer. The strongest carbon-nitrogen bond is this one. It's a triple bond. Just for kicks, we can do the rest of them. We've got a carbon with 3 hydrogens, and it's next to a nitrogen, and it's just going to be a single bond because it's already got 4 bonds now. And that nitrogen is connected to 2 hydrogens. So 3 bonds to the nitrogen. The last one, 3 hydrogens connected to a nitrogen, and then to an oxygen, double bond to oxygen. Oxygen needs 2 bonds, nitrogen needs 3, carbon needs 4. I mean, those guidelines are to have formal charges of 0 on your atoms. All right, if you don't have any of the fancier elements, row 3 or anything like that, if it's just carbon with a few other things, try these shortcut rules. They help. And don't forget, there's lone pairs I didn't draw. Right? There's a lone pair there, there's a lone pair there. Yeah. Oh, and here. Okay. But then the answer is B. Okay. Nitrous oxide, which of the following is the correct Lewis structure for the compound. So hopefully you've seen this enough in the homework, in the labs, to know what the correct answer is. The correct answer is C. So first of all, the nitrogen is in the center, which is fine for all of them, but This is the only one where you get a formal charge of plus on the nitrogen and minus on the oxygen. And that's it. That's like the fewest formal charges you can have. And the negative formal charge that has to be there is on the most electronegative element, which is the oxygen in this case. The other common way to draw this, which is incorrect, is this one. And if you do it this way, you have a negative formal charge in the nitrogen and a positive formal charge in this nitrogen. But having a negative here is not as good as having a negative here. So negative formal charges should be on the most electronegative element. So C is the correct one. So if X is a third row element and it has this Lewis structure, X must be what? Well, there's a few ways you could do this. You could just try all of these elements and see if they make sense. Or you can count electrons. So remember that the Lewis structure should show all of the electrons. And so I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, if I counted right. 26 total electrons. And I know that 21 of them come from the chlorines. Right? Chlorines bring 7, they're group 7, and there's 3 of them. So 3 times 7 is 21. So from the chlorines, there's 21 electrons. That means there's 5 left. So that X element should have 5 valence electrons. That's where those 5 came from. And the only one that fits there is phosphorus. Phosphorus has 5 valence electrons. It's row 3. So C. Okay. My finger's too fat for this. All right. Which of the following elements would form a compound with the following Lewis structure? So this is the same kind of question. Which of those fits in the X spot? So we'll do the same thing. Count electrons and see what matches. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18 total electrons. And let's subtract. We know there's an oxygen that brings 6. And we know there's a chlorine that brings 7. And again, we have 5 left. Looks like phosphorus again. The only one that fits. So those 5 valence electrons left come from the phosphorus. All right, that's yeah, hopefully that's clear. Which of the following species contains only single bonds? So, got to draw it out again. And again, you're welcome to do the original rules for Lewis structures that we learned in lab. Which actually might be a good idea in this case because you have all these charges. But if you do that, well, so we'll do Cn real quick. Cn minus 4 electrons from the carbon, 5 electrons from the nitrogen, plus an extra electron because of the minus charge, that's 10. We'll do a skeletal structure first. Put a single bond between them, 2 electrons. I've got 8 left. So 1, 2, 3, 4, 5, 6 on this carbon. I've got 2 left, 1, 2, and I've got none left. I don't have enough to satisfy the octet rule on this nitrogen. I need 4 more. So I'm going to take this pair and make a triple bond. So that's got a triple bond, no single bonds. If you keep going, oh man. Well, I know CO. Let's skip B for a second. Well, let's just do B, fine. NO plus. NO plus, it's got 5 electrons from the nitrogen, 6 electrons from the oxygen. The plus charge means we are losing an electron. So 10 total electrons. NO, got 8 left, and now we've got the same scenario as we had up here. So we end up doing a triple bond between them. Believe me, that's how it works. So I can keep going. O2 2 minus. That's a fun one. So CO I know is this. And you're welcome to try it yourself. That's what CO is. O2 2 minus. 6 electrons plus 6 electrons plus an extra 2 from the charge is 14 electrons. So we'll do a bond between them. And then I need 1, 2, 3, 4, 5, 6. And I need 1, 2, 3, 4, 5, 6. Sorry, we're running out of room here. I've got 0 electrons left, but that's fine. Everything's got an octet rule set. That's the charge. I mean, that's the Lewis structure. A single bond between the 2 oxygens. This is not normal, right? Regular oxygen has a double bond, but this is an oxygen with a -2 charge to it. So that's it. That one contains only single bonds. E does have single bonds in it, but the CO is a double bond. If you try that, you'll get that. Okay. So which of the following would be a resonance contributing structure for the compound? Note lone pairs are omitted, but everything follows the octet rule. So let's just draw those in, so it's complete. So if everything obeys the octet rule, there's 2 lone pairs here, there's 3 here, and there's 1 there. So the only other resonance structure that would make sense, you cannot move the atoms around. The Z has to be in the middle. So B and C are out. And if everything obeys the octet rule, we know there's a lone pair on this Z. I can't move this lone pair here to make a double bond because that would put too many electrons on the X. So what's happening here is I have to move this back to the X, and then this is going to come down instead, over here. So if I do that, I get like that, something like that. So the only one that makes sense here is D. That is the other resonance structure. And I think hopefully that makes sense. I mean, you see these patterns where the double bond. If you've got 2 of the same atoms, why is the double bond on this side? Why can't it be on this side? Well, that's the idea. It's could be on either. In fact, it's both, or at least it's not. It's neither. It's a 1.5 bond to both sides. That's what the resonance hybrid looks like. Okay. Which of the following molecules is best described with just 2 resonance structures? So when we're talking about resonance structures in this case, they need to be equivalent resonance structures, not one where it's very stable and one where it's very unstable. They have to be equal resonance structures. And if you have done any of the homework or done any of the, followed along in any of the lectures, hopefully that first one, nitrite, looks a little suspicious. Looks like it could be it. If you draw this out, you'll get this. And you might not get that. You might get the opposite. You put the double bond here and the single bond here. And that's the resonance structure. So you could either have the double bond on the left side or the double bond on the right side. And those are it. Those are the only 2 options. We did nitrate in the lecture. Nitrate has 3 oxygens. This one only has 2. And as a result, you only have 2 resonance structures. And that's it. So hopefully you do the first one and you get the answer and you ignore the rest. Because the rest of them only have 1 structure that makes any sense. Okay. Use formal charge to decide which skeletal structure gives the most favorable Lewis structure of the molecule. Okay. This one's not hard. I think you can tell which one is the better structure just from kind of general rules about how many bonds things should have. So if I calculate the formal charge on this thing, this carbon, it's 4. So the number of valence electrons, 4. There are no lone pair electrons. And there are 2, 4, 6, 8 bonding electrons. So that's 0. And on the oxygen itself, 6 valence electrons originally, minus 4 lone pair electrons, minus 4 electrons in bonds, and this is also 0. So that looks like the right one. Just to be sure, if I drew it like this, this oxygen is 6 valence electrons minus no lone pair electrons minus half the number of bonding electrons. There's 8 bonding electrons, so 6 minus 4 is a plus 2, which is pretty bad. And this should be minus 2, because all of the formal charges add up to the overall charge. Should be adding up to 0, because this is neutral. But if I do it, 4 minus half of 4 is a minus 2. So it's the left one. That's the correct one. Just based on these formal charge calculations. You should show your work, please. So if they say show your work on the exam, please show some work, so a formal charge calculation that proves that you knew what the answer was, without a guess. All right. So this is a Zwitter ion. If you take any bio or molecular biology or something and you studied amino acids can be drawn 2 different ways. One way is the neutral way, normal way. Another way is this Zwitter ion way. And in a Zwitter ion, there are intentional formal charges, a plus and a minus in them. There is a positive charge on the nitrogen group on the amino backbone, which we can ignore. What about the nitrogens labeled 1, 2, and 3 on the side chain? Use the formal charge to determine if they are neutral, negatively charged, or positively charged. So, this nitrogen here, we do the calculation, 5 valence electrons, this is nitrogen 1, 5 valence electrons minus 2 lone pairs minus half the number of bonding pairs, so there's bonding pair electrons, so 6, 0. With nitrogen 2, I kind of gave it away, there are no lone pair electrons, and there are 8 electrons in bonds. 4 bonds, 8 electrons in those bonds, plus 1. And then for the last nitrogen, nitrogen 3, that's exactly the same as this kind. So 5 minus 2 minus half of 6, 0. So it looks like A is the answer. Anybody see where the other formal charge is in this molecule? So there has to be a minus formal charge in there somewhere. If this nitrogen has the positive formal charge, there's a negative somewhere. Actually, there's another one here. There's actually 2 of them in here. But the other one is there. There's a negative there. This is actually not neutral. That's weird. I feel like there's a mistake in here somewhere. Anyway, this is fine. The problem works. Which best describes the shape of the I3 minus ion? So this one won't be in the exam because this involves an expanded octet, or at least it's part of the naming of this expanded octet. But this one happens to be linear. So if you see this one, if you've done this one in the lab, not everybody got to do that one. You do that one real quick. I3 minus. Each iodine is 7. There's 3 of them, and then there's an extra 1 from the charge, 22 electrons. I'll put 1 iodine in the middle, and then iodines on either side. And it's not linear because of that, but I'm just setting it that way. 2, 4, 18 left. I'll do the octet rule on the outside. I'll do the octet rule here. So 6 plus the 2 is 8. And then I'll do the octet rule in the middle. So I just need 2, 4 more. 6, 8. I've used 4. I've got 2 left, and I have to draw those 2. There's no way to not draw them. I have to put them in. So if you didn't put them in, you might guess this wrong and say it's bent. But once you put them in, the extra 2 go on that central iodine. That iodine can have an expanded octet because it has empty d orbitals. So the electron geometry is trigonal bipyramidal, and the molecular geometry for this is linear. So again, I won't give you this on the exam, but that's how you do that one. It's linear. SF3 plus, you can do that one. This works better. Yeah. SF3 plus. So 6 electrons from sulfur. It's in group 6. 7 electrons from fluorine, and there's 3 of them. Not plus, minus. We are losing an electron from the plus charge. Minus of electron because of the plus. So 20 plus 6 is 26. Sulfur, fluorine, fluorine, fluorine. That's 6 electrons in those bonds. We'll do the octet rule for the outer atoms. 1, 2, 3, 4, 5, 6 plus 2 is 8. 1, 2, 3, 4, 5, 6 plus the 2 is 8. 8 left. And then 1, 2, 3, 4, 5, 6 plus those 2 is 8. I've got 2 left, and I need to do the octet rule for the center. Boom, done. Those 2 get used up. I've got an octet and everything. Pretty happy. So, the shape of this thing. Well, 1, 2, 3, 4 separate electron domains. The electron geometry is tetrahedral. But the molecular structure, the shape of the molecule, what you would call that molecule shape, is not that. The molecular geometry is trigonal pyramidal. It's one of the subshapes of tetrahedral. Okay, so this is the one that looks like a pyramid, a tripod without the top part. Well, it's a tripod, yeah. Okay. Okay. You can tell when this question was written, or maybe you can't. There was an anthrax scare a decade or so ago. Somebody was mailing anthrax to important people across the U.S. It was pretty bad. Little envelopes full of powder that looked like flour, but it was actually anthrax. Anthrax is transmitted via spores, I think. Anyway, we used this antibiotic, Cipro, short for ciprofloxacin. It's another made-up name, but that's what it looks like. What are the formal charges on the nitrogen's label? So the more you do these, the more patterns you start seeing. I see 3 bonds to nitrogen with a lone pair. That's normal. That's got a 0 formal charge. This nitrogen, 3 bonds to nitrogen with a lone pair. That's the regular one as well. 3 bonds to nitrogen with a lone pair. They're all 0 formal charge. You could calculate it manually, and you'll see it's all 0. So, see. Giant, scary-looking question that was pretty boring answer. All right. Which of the following molecules has a trigonal planar shape? These are the worst because you gotta kind of draw them all out. But trigonal planar, you can eliminate some of them. You need 3 things bonded to a central atom at least. So you can get rid of A, you can get rid of C. So we have to look at B, D, and E. Okay. So if we look at B, PCl3. That's going to be phosphorus with 5 electrons, and then 3 chlorines with 7 electrons each, 26. I'll do this fast. This is what you get. That's not trigonal planar. That is going to be trigonal pyramidal because you've got 1, 2, 3, 4 groups of electrons. That's tetrahedral electron geometry, and one of the subshapes of tetrahedral is trigonal pyramidal. So that's, if I were to draw this out, it looks like this. I'm looking for the one that's flat. There's 3 in a flat circle with 120 bond degrees. 120 120 degree bond angles. I'm saying that all backwards. If you were paying attention in lecture, you might remember, hey, BF3. That sounds familiar. So boron has 3 valence electrons. Fluorine has 7, and there's 3 of them. So 21 plus 3 is 24. If I do the Lewis structure, I get that. 6 electrons total that I've drawn in so far. Octet rule in the outer. Octet rule here. And octet rule here. And I'm out of electrons, but that's okay because you should remember in the back of your mind, boron is one of those elements that actually is okay with not a full octet. So having 6 electrons around boron is not going to hurt it. And even if you didn't remember that and you tried to do a double bond, that's okay. It won't be the right Lewis structure, but you'll still get the right shape. So I've got 3 groups of electrons around the boron. That's trigonal planar. That's the answer. Okay. Not fast. Tell me to slow down if I'm going too fast. All right. Which of the following molecules are planar? All right, so planar. We're looking for trigonal planar. We're looking for bent. Bent is planar. We're looking for linear. All of those are planar. We're looking for things that are not going to, if I put it in a flat plane in a piece of paper, it'll have any perspective going in and out kind of thing. So, we draw all these. SO3. Oh, this is so many. So 6 for sulfur, 6 for oxygen. That's 6 times 4, 24 electrons. It's going to kind of look like this. So I'm going to speed things up. It's going to look like this. I think only 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, yeah. So it's going to look something like that. And you might argue, oh, well, we could probably reduce the formal charges a little bit. But that's okay. This works. Because we have 1, 2, 3 groups of electrons, trigonal planar. So 1 is definitely planar. If I switch to SO3 2 minus, this is better known as sulfite ion. What's happening is I have 2 extra electrons. So 26 electrons. So what I would end up having to do if I did this over again is, instead of sharing electrons like I did here, so that I have an octet here, I actually have those 2 extra electrons, and they would go right there. So that's not planar. That is tetrahedral electron geometry, and then when you do the molecular geometry, it's trigonal pyramid. So that's not planar. I mean, it looks like this. If you ignore anything else. So that's not planar. 2 is not planar. We've done nitrate before in lecture. That one is definitely planar. That one, if you draw this out, you'll get trigonal planar, just like we did up here. So nitrate looks just like this one. NO3 minus looks like this one. 1 and 3 are definitely planar. And the only one that does 1 and 3 is this one and this one. So let's check with number 5, letter V. BH3. Well, BH3 is actually a lot like this one, without the lone pairs all over. So BH3 is going to be just like this, just like BF3. And if you count the electrons, that's really all you have. Boron has 3, hydrogens have 1 each, so 3 total, 6 total electrons. 2, 4, 6, that's it. And this is a case where boron can have fewer than 8 to be okay, to be stable. So that's planar too. It's trigonal planar. So 5 is good too. So C is the answer. 1, 3, and 5 are all planar. They all happen to be trigonal planar. PF3, we didn't do that one, but PF3 is going to look a lot like, this one. This is PCl3. So we're just replacing chlorine with fluorine. They're both halogens. They have the same number of electrons. Oop. So metformin. It's a drug. Lowers blood sugar levels. So this is what metformin looks like. It's a really weird compound. Use the electron domain model to predict the geometry around the nitrogen at the center of the molecule. So using electron geometry, what is the electron geometry around that nitrogen? So 1, 2, 3, 4 groups of electrons around the nitrogen. That's tetrahedral. That's not what we would call the shape. The molecular geometry would be trigonal pyramidal, but the electron domain geometry would be tetrahedral. Okay? So be careful what we're asking you for. Shape of the molecule, just generically, what's the shape of the molecule? That's the molecular geometry. All right? But anything else will have to be more specific. All right. We have a Lewis structure for SO2. And if I were to give you the average bond length for a SO single bond, it's 157. The average bond length for an SO double bond is 135 picometers. What would you predict the bond length between these 2 atoms to be? So the trap answer is A. That's the trap. Do not answer A. Why? Because you should see this and you should say, there is resonance structures here. That SO2 molecule could just as easily have been drawn with the double bond on the other oxygen. Like that. So these are the 2 resonance structures. And the actual bond length is going to be closer to what the resonant hybrid looks like. So the combination of those 2 resonance structures. So on average, so if you look at one of these resonance structures, what is the average bond order going to be? Well, there is a single bond and there is a double bond. And that's spread out over 2 bonds. So 3 over 2 is 1.5. The average bond order is 1.5. So the true picture of this molecule is a 1.5 bond to each oxygen. Let me just not draw the little pairs in. So what would I predict? Well, if it's somewhere right in the middle, that's what the bond order is going to be. So if I average out those two numbers, 135 and 157, divide by 2, is it 146?
C.
Yeah, it makes sense. Okay, 146. So I would predict that the actual bond length in that molecule is going to be 146, somewhere in between. Okay, so this is like understanding what resonance is for, what it does, how to visualize what the molecule really looks like. All right, we have a new one. Structure A, structure B. Which contributing structure is the larger contributor to the hybrid structure for this molecule? So these two are resonant structures. All we're doing is moving electrons around. We're not changing any of the positions of the atoms. So they're actually resonant structures. But are they equal resonant structures? Not like before. The one we looked at before, they were pretty equal. There's no difference between them. But here there is. How do we tell? Formal charges. We calculate a formal charge in all of our atoms, and we see what we get. If you do that, you will get 0 formal charges on everything except for the carbon here. You'll get a minus formal charge in the carbon here. And then you'll get 0 everywhere except the oxygen. You'll get a minus on the oxygen in this structure. So is it better to have a minus on the oxygen or the carbon?
Oxygen.
On the oxygen. You want your negative formal charges on the more electronegative element. So structure B is going to be the dominant, the most contributing, the resonant structure that contributes the most to the hybrid structure. All right, so structure B is the answer here. So if you had to predict what the CO bond length is going to be, it's going to look a lot like this one, because this is the dominant resonant structure. So 143 is your option, and I would circle 143 because I think that is a much more stable version of the structure than the structure A is. Okay. Yeah. In reality, is it exactly 143? It might be 141, a little bit closer to the double, but not even, not halfway at all. Okay. All right, this is back to a little bit older stuff, I think. No, this is new. Average valence electron energy. Can you guys calculate that? Remember how to do that? So to calculate an average valence electron energy, you have to consider all of the valence electrons for an atom. So for phosphorus, let's do just for fun, we'll do the electron configuration. It's 1s2, 2s2, 2p6, 3s2, 3p3. That's phosphorus. So the valence orbitals are just these. So we're looking at these electrons as the valence electrons. And I have to consider all of them, all of their ionization energies to calculate the average valence electron energy. So to remove the first electron in here, it would be 1.95. To remove the other electron in here, 1.95. What about removing one of these? 1.06. But there's 3 of them. So the second one is this, the last one is this. And I'm going to divide that by 5 total electrons. And that will give me the average valence electron energy for that element. Which I have no idea. What is it? Is it D? B. No, it's B. Yeah. B. Okay, thank you. It's too close to the 3s. All right. All right. compare the following molecules, which molecule will the partial charge on fluorine be the most negative? So the partial charges come from the difference in electronegativity, right? The closer they are together in electronegativity value, the less dramatic the difference in charge is going to be. So we want the biggest difference in charge. So fluorine is the most electronegative. We're looking for the least electronegative. That's going to look like silicon, I believe. Silicon is furthest to the left, furthest down the periodic table. So francium down at the very bottom left is like the least electronegative. So we're looking for left, down. And that would be silicon in this case. Silicon is the least electronegative. Fluorine is the most. That difference is going to give us the biggest difference in electronegativity. It's going to give us the biggest polar bond possible. So largest partial negative on fluorine will be from there. Okay. If I have a compound that is trigonal planar, what's the hybridization? This is memorization. sp2. All right, linear is sp. sp2 is trigonal planar. Tetrahedral, sp3. So we're talking about electron geometry, okay, not the molecular one. All right. 62. How many atoms are sp2 hybridized? I'm going to have to redraw this because I can't draw on the screen. So, boom, boom, boom. Okay. You have to get comfortable with line drawings. Remember that hydrogens are not shown. And these are not Lewis structures. We are not showing lone pairs. You have to, they are implied. Right? This oxygen has two pairs of lone pairs on this thing. There is a hydrogen here. There's a hydrogen here. There's nothing there. There's a hydrogen here. Hydrogen here. There's a hydrogen here. So you kind of have to understand all this. So I will. We're looking for anything that has three groups. So I mean, I can show you that if I put the hydrogen there, there's 1, 2, 3 groups of electron around that carbon. That's trigonal planar. That's sp2 hybridized. So that carbon is hybridized. That one is sp2. That one's sp2. That one's sp2. 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 This is the same. There's a hydrogen here. There's a hydrogen here. There's 3 groups of electrons. 1, 2, 3. sp2, sp2, sp2. Everywhere I drew an X is an sp2 hybridized carbon, all trigonal planar. 1, 2, 3, 4, 5, 6, 7, 8, 9. So E. How many pi bonds are there? So pi bonds are everywhere we have a double bond. All right, this double bond is made up of a sigma bond and a pi bond together. That's what makes the double bond. So pi, 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 pi. Looks like 5. We are ignoring the whole idea of resonance at this point, as if you include that, that would make this discussion very complicated. But literally what's drawn in this structure is 5 pi bonds. Okay? There we go, 5. How many sigma bonds are there? This one's tricky because people just look at what's drawn. Don't forget all the hydrogens too. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I think I did them all right. There's 18 sigma bonds. I mean, yeah, don't forget all these hydrogens that are on here. These are all connected with a sigma bond as well. And the double bonds have a sigma bond in them too. The double bonds are both sigma and pi together. What is the bond angle around the oxygen atom? marked with a, that's not an oxygen, but the oxygen's up here, marked with a pound sign, or a hashtag, everybody likes to say now, or a sharp if you're a music person. What is the bond angle? Wait a minute, that doesn't make sense. I guess it's a misprint. It should be around the carbon. So what is the bond angle around this carbon that's here? If it's sp2 hybridized, it's trigonal planar, it's 120 degrees. We're not asking for distortions at this point, but you know, it's approximately 120. It's not going to be perfect, because there's 3 different kinds of atoms there. There's a double bond, the double bond pushes harder, but approximately 120. What is the geometry around the carbon atom marked with a star? Trigonal planar. We've just mentioned it multiple times. It's not bent. Don't forget the hydrogen. There's a trigonal planar thing there too. I mean, it's trigonal planar because there's the 3rd atom there. Okay, what types of electrons are considered to be localized between 2 atoms in valence bond theory? So this is just understanding what localized electrons mean. That means that these electrons are stuck. They're definitely between these 2 atoms. And that occurs in sigma bonds. In sigma bonds, those electrons are there. That's all they can be. They can't be shared with any other orbitals. All right? Pi bonds don't have that restriction. You can have multiple p orbitals that kind of stack side by side by side, and you know that's what happens in benzene. You get delocalized electrons, but for localized electrons, these are the ones in sigma bonds. And it's not true that all electrons are localized. Valence bond theory does include delocalized electrons. Oh, I did. Cool. Okay. So we've got O and S negative. What is the Lewis structure, and what is the best one if more than one? You guys feeling more ready? Kind of repeating a lot, right? There's only so much we can do. But O and S, take a hint as to the clue as how we're writing these letters. And if you're not sure, also remember that the least electronegative element goes in the center. So that N definitely goes in the center. We were going to put oxygen and sulfur around it. Oh, I got it backwards. That's okay. The total number of electrons, 6 from the oxygen, 5 from the nitrogen, 6 from the sulfur, plus an extra 1 from the charge. That's 18. So 2, 4 already drawn in. And then we'll do octet roll. 8 left. Octet rule. 2 left. We'll put those 2 here, but that's not enough. I need 2 more electrons. So this is where resonance comes in, or at least resonance structures. They're probably not equal. I need an extra pair of electrons. I can share it either from the sulfur or from the oxygen. And in fact, I'm going to try both. So let's move these over here first. I'll put the double bond here. And then I'll draw another structure where instead of putting it from the sulfur, I'm going to pull it from the oxygen. And put a double bond there. So this is untouched. These are the 2 different resonance structures. And if you're going to draw it, technically we have to put a bracket minus around them, because they're negative. As far as which one's better, formal charge is going to tell us which one's better. So if I calculate a formal charge over on this oxygen, I get a, here I'm not going to do it because we're running out of time, but I'm just going to tell you the answer. We get a minus formal charge on this oxygen, and if we do it down here, we get a minus formal charge on the sulfur. Everything else is 0. So hopefully that settles which one's best, because the negative formal charge needs to go in the most electronegative element. And I don't need a chart to show me that oxygen is more electronegative than sulfur. It's closer to fluorine. It's top up to the right. Those are the most electronegative. So this is the correct structure. I should have circled it, but that's the correct structure. And then you have to explain, so you can talk about how the negative formal charge goes in the most electronegative atom. Sketch the shape. I get 1, 2, 3 groups of electrons around that nitrogen. So that's trigonal planar electron geometry. The molecular geometry is not the same though, because there is not a bonding, this is not a bonding pair, it's a lone pair. So really what we're left with is a bent shape. Right? We start off with this trigonal planar shape. Right? So trigonal planar around the nitrogen, 120 degree bond angles. There's an oxygen here, it's a sulfur here, and there's nothing here. Just a lone pair. So we keep that bent shape. That's what it looks like. What are the bond angles? So the bond angle from here to here is approximately 120 degrees. Probably a little less, because lone pairs push a little bit harder than bonding pairs do, but that's good enough. What is the hybridization around that nitrogen? Since it's trigonal planar electron geometry, it's sp2. That's it. Trigonal planar, sp2, automatically. Is it polar or nonpolar? I would say it's pretty polar. And you don't have to kind of fool with the bond dipoles if you want. You can get it from the fact that it's not a symmetrical shape. The electron geometry and the molecular geometry don't match. That's one of the requirements that I put down on the board for you guys. They have to match to be nonpolar first, and then the outer atoms have to be the same too. So that is not even true. So this is definitely polar. You have a question? Yeah.
Yeah, is that where the II3 ion was linear because they were the same on the other side?
Oh, so it was linear because there's 5 groups of electrons around it, and when you do 5 groups of electrons, you do this trigonal bipyramidal shape. Right, that's the trigonal bipyramidal shape. There's 3 around the middle, 1 on top, 1 on the bottom, and 1 iodine goes here, 1 iodine goes here, and then these are just nothing. They're lone pairs.
Okay.
So linear because of that.
Okay.
Like I said, I won't ask you this particular question because it's trigonal bipyramidal. I'm not going to put that in the museum.
Thank you.
Okay. I think we're done. Electron configuration. This is all old stuff. All right, I think. Oh, draw an electron orbital representation for HCN. We can do that very quickly. So, and you can definitely do this with multiple pictures. You don't have to do it all in one diagram. But HCN, let's draw the Lewis structure first. HCN, and I'm taking some shortcuts here, but it looks like this. That's HCN. And immediately what you say is, hey, that's linear. So it's sp hybridization around the carbon. So knowing that, I'm going to start with a carbon in the center, and there's going to be an sp hybrid orbital pointing that way, and an sp hybrid orbital pointing that way. And on this side, there's going to be a hydrogen with a 1s orbital. And on this side, there's going to be a nitrogen with just a regular p orbital. It's a 2p orbital. All right, that's not hybridized, just a regular 2p orbital. So those are the sigma bonds that form, right? The end-to-end overlap. All right, sigma bonds. Those are the first bonds. So there's only a sigma bond there, but one of these bonds in the triple bond is a sigma bond. Now after that, since this carbon is sp hybridized, there is 2 unused p orbitals. So let me draw that separately so it's not kind of a big mess. And there is a p orbital in the nitrogen as well. And the p orbitals kind of go this way and this way, and I didn't draw it very well, but they overlap side to side. And this is what is known as a pi bond. So that's the second bond in that triple bond. The third one is another pi bond. And, you know, however you want to say it, it's basically rotate this 90 degrees. There's another p orbital going this way, in and out of the board. And they kind of align parallel this way as well. So there's 2 sets of these. And that's what all the bonding looks like. So clearly label each orbital as sp, d, f, sp, sp2, sp3. Yeah, I think I've labeled everything. Oh, so these are 2p orbitals. So that's kind of how you want to draw bonding. Do your best. Show, you know, label everything as important so that I can tell the difference between a little blob that is a p orbital and a blob that is a sp hybrid or sp2 hybrid or something like that. All right, any questions on any of this? That was a little bit tricky, I think. You're welcome to try to draw this all into one picture, but it would get a little bit messy. That's why I separated it. And if you're like, I have no idea what this is, and you don't have time to study it, it's one part of the exam. It's not going to kill you if you don't get it right. Focus on your strengths. If you have something that you just need to work on a little bit and you'll master it, do that. You want to make sure you get the points where you can get the points definitely. So come back to this once you've exhausted all the other avenues if this is really tough. All right, I think we're going to be done. Time to go. I can stick around for a few more minutes if you want me to solve anything or ask questions.